We hear a great deal these days about computer-aided design. All manner of marvelous things, ships, hotels, hospitals, can be designed and assembled on a computer terminal. I wonder if you've had any thoughts as to what this creation, which my colleague Dr. Andreas Novak has placed on the screen, is about. Do you have any ideas? If we rotate that slightly, perhaps you might have some thoughts. Here we are. We see some cavities inside there. Let me just show you a three-dimensional model of that. Here it is, a three-dimensional model, these large cavities. Now, it so happens that this drawing of that structure is for a new building that comes out from a book in the Department of Architecture in the Israel Institute of Technology. If I show you this drawing is exactly the same as that creation that we have there. But what this actually is the architecture of a rare mineral which you can mine in Bavaria. In fact, it's also the structure of one of the world's most widely used catalysts. What do I mean by a catalyst? A catalyst is an agent which accelerates change. People can be catalysts. If you're interested in transporting food, shall we say, to Africa, then you can think of Bob Geldof as a catalyst. The catalyst that I'm talking about, the one that has this structure, is a material that you can convert from clay, which in turn acts to convert oil into petrol. Now, the amazing thing about architecture of crystals, which is what we're going to be talking about, is that it has a very long history. There was a brilliant Englishman named Robert Hooke 300 years ago. He started asking the question, why is it that a crystal such as this, Iceland spar, this is called, or calcite, or limestone, or calcium carbonate, they're all the same thing. Why are they so smooth? And why are the edges so sharp? Now, Robert Hooke was a very, very clever man, and he published 300 years ago this very famous book called Micrographia, one of the most important in the history of science. Here's the front page. Now, in it, he describes many, many things that he saw under an optical microscope, a very new instrument in those days. I think we should begin today by asking a volunteer to come along. If I could have a volunteer who would be willing to come along. What about you in the red jumper here? Come along. What's your name? Russell. Pardon? Russell. Russell. Good to meet you, Russell. Now, I want you to help Paul, who is going to handle this magnificent machine, a scanning electron microscope. What we've done is to place into this microscope fragmented portions of this crystal of calcite, because we're going to try and show you the kind of view that I'm sure would have given great pleasure and rapture to Robert Hooke. If we can move what we see on the screen there it is, three-dimensional view of very, very minute fragments. We have a magnification of approximately 300 or so. And the most noticeable thing is that you'll find that there are fixed angles. That angle there is exactly 78 degrees. And this angle here is exactly 102 degrees. And in fact, whatever the size of the crystal, however small it is, or however big it is, here it is, it's 102 and 78. Why is that so? Wondered Robert Hooke. Well, he gave it some considerable thought, and this is the conclusion that he reached. See, he looked at these minute crystals under a microscope. And then he deduced that just as the Greeks had imagined that there were small spheres, economically packed, they must be rather like this. And that's the reason why you get sharp edges and sharp corners and smooth faces. Well, perhaps the notion of smooth faces isn't immediately obvious to you. Let me try and explain it with the aid of a little movie clip. Thank you, Russell. You've done us well. Thank you very much. Look at this. You know what these are. Tell me what these are. The pyramids, exactly. We're in Cairo, in Egypt, just outside Cairo. Now, those faces of those pyramids look smooth from a distance. They look very smooth from a distance. The closer we get, look what happens. They now appear to be really quite rough. Now, if we had the ability to look at this crystal very, very, very closely, or put it this way, if we could enlarge what's there so that we saw the final constituents, saw those atoms, what we would see would be something like this. Now, that doesn't feel too smooth to me now because I've blown up, if you like, the size of the atoms. But from a distance, if I were to go very, very far away and look at it through a telescope, that would look pretty smooth. Now, that's the essence of the conclusion and the idea that Robert Hooke had. He wasn't alone in that idea. It had come much earlier. It had come much later. There was a Londoner, a man from Islington, who was a gentleman scientist, an estate agent, William Barlow. He said that copper, metallic crystalline copper, was made up like this. Very nicely packed layers, one on top of the other. Notice, if you look very carefully, the first layer and the fourth layer coincide. There's 1, 2, 3, and then the fourth is exactly over the first. Now, if I take that away and start pulling this apart, look what I've done. I've got the smallest repeat unit. There are 13 atoms there. There's a slightly larger view of it here, look. 1 in the middle, 6 surrounding it, 3 at the bottom, 3 at the top. That's what I've got here. And indeed, I can think of all this as being made up of a very large collection of 13 atom clusters. That, said William Barlow, is what copper is like. Was he right? We're going to try and find out. Let's put that aside. And now, Bryson and I are going to carry out an experiment, but not before I tell you with what material. Here I have a mineral which has been known since antiquity, graphite. It's a very black, glistening mineral. You can write very easily with it. That's where we get the word autograph and graffiti and graph, because it's the Greek for this, graphos. Very soft, and it's a good lubricant. What is its structure? This comes from a town in New York, in Ticonderoga, in fact. If you were to fish out from there a very small flake, it would look something like that if I enlarged it. A flake of graphite would look rather like that. Now, what we are going to do is an experiment which takes us into the realm of what may appear to you to be a little strange. I can assure you it's not strange at all. It's diffraction. We've got electrons. You may remember from lecture 1 that we can have electrons that can travel through an evacuated space, and we're arranging for those electrons to penetrate, to go through this flake of graphite that we've put in there. It goes right through the graphite, and then it produces, lo and behold, very, very nice image, a central spot and 1, 2, 3, 4, 5, 6 spots surrounding it. If you look at any one of those spots, there are 6 spots surrounding it. Now what's happening? Well, let me remind you what Professor Phillips told you last time. The electromagnetic spectrum. Light can be sometimes like waves and sometimes like little bullets. Electrons can sometimes be like little bullets and sometimes like waves. Now, the only difference between light and X-rays and electrons is a matter of wavelengths. So what Bryson and I are now going to do is to sort of redo that experiment, not with electrons, but with light, with laser light. Switch on the laser light, please, Bryson. Let it bounce against that mirror, and let it hit that screen there. I'm going to take hold of this little object, and I look at it very carefully, and what I see is what you should see on that screen. That's it. It's a sort of square mesh. Now, Bryson, if you'd be so good, let that interrupt the path of the laser beam. Now, look what happens. There's a square mesh of red dots. Now, that's not just a shadow, you understand. I mean, there's been a considerable scattering. That really is diffraction. That's what it is. Now, obviously, that's not the pattern that we got back there a moment ago. We had a hexagonal pattern back there. How can we arrive at a hexagonal pattern? Well, now, I'm going to see what would happen if I put this in. Let's see what this would give us. There we are. There we are. We have a hexagonal diffraction pattern. Can I have a look at that, please? And you will see on the screen what I'm going to see, I hope. That's right. Now, we should see, thank you, Bryson. Look, something very significant. This is a mesh in which I have a central atom with 6 atoms surrounding it. Any one of these, a central atom with 1, 2, 3, 4, 5, 6 atoms surrounding it. Now, cutting a long story short, what I can say to you, therefore, is that graphite, if it gives rise to this hexagonal pattern, the type that we saw with light, must be in 2 dimensions like that. It's got to be. It's got to have an arrangement of carbon atoms. It's just solid carbon. It's got to be like that. So that's the 2-dimensional architecture of graphite worked out. Fine. Let's find out what the 3-dimensional structure is. Now, instead of allowing the electrons to go through that way, I could orient this in that instrument back there such that the electrons would come through this way. And then by looking at the pattern again, we could work backwards. And that was done. It was first done, in fact, in this building in 1924. And the 3-dimensional structure of graphite was worked out. And here it is. The 3-dimensional structure, I just push that ever so slightly forward so that you can compare this hexagon with that hexagon, or this net, this 2-dimensional net with that one. See, 1, 2, 3, 4, 5, 6. A sheet and another sheet and another sheet. Now there's something very interesting here. If I tilt this, look what happens. You now see in all its glory that lovely layered structure. That's why it's a good lubricant. That's why it's so soft. That's graphite. 3-dimensional structure of graphite. Well, we don't have to stop at graphite. In fact, my predecessors, Sir William Bragg and Sir Lawrence Bragg, they were the first to work out this strategy, to really show that you could get at the architecture of crystals by, in fact, pushing through beams either of electrons or of X-rays or of light. Now, I'm going to have this other model. This is the model built here in 1924 by Sir William Bragg of diamond. That's the diamond structure. If I had eyes which were good enough. When I look at this Cullinan diamond, the model of the Cullinan diamond, the largest diamond ever mined, 3,000 carats, if I could really see inside, and I can do it indirectly with X-rays and electrons, this is what I would see, the diamond structure. And incidentally, if I could do likewise with copper, I would confirm that our friend William Barlow was correct. That is indeed the structure of copper. I'll tell you something more. It's the structure of gold. Let me explain. Here's some British gold, to be precise. It's from mid-Wales. It's from Dolgellau. That's the gold that the British Museum Natural History has allowed us to take out from their reserves. Look at that. Lovely gold which the Romans mined when they came here. The structure of gold is exactly the same as the structure of copper, except that the atoms weigh 3 times as much. They have the same architecture, but different building blocks. You might say that one building is made of concrete, one of wood. One is made of copper, one is made of gold. 3 times as heavy. That's fine. Now, these models that have been built with loving care, they take time. They're very important. They're extremely valuable. One can also put models on a screen. Watch what Andreas Novak is going to do in a moment. Here's the crystal structure of diamond placed on our computer graphics screen. Now, you can see as he rotates it that each carbon atom, which now we represent as orange colored, has got 4 other atoms attached to it. That's the diamond structure. Don't go too far, Andreas. Just a little bit more, perhaps. Just a little bit more. Fine. Stop there. I've asked him to stop there for a good reason. I think you can see that it would be relatively easy, at least conceptually, in one's mind it would, to part the crystal there, to cleave it, rather than doing it this way. And in fact, that's what the clever diamond merchant, the man in Amsterdam or in Antwerp or in New York, who looks at a diamond, he sort of divines where it is that he has to cut. I wouldn't like to be entrusted with that responsibility, to cut that Cullinan diamond. It is said that the man who did cut that, after thinking about it for 3 days and doing it, he fainted. And I can understand why. That's diamond. Now, we're going to change these atoms. We're going to change them, as Andreas will do shortly. Watch it coming up. Here we are. We've got the same structure. You'll note it's exactly the same structure, but the color of the atoms are now different. Now we've got arsenic in this sort of yellow-green. We've got gallium in the blue regions. Yellow-green, blue. Gallium arsenide, that's the material which we use in fast computers, which we use in lasers, which I mentioned in the last lecture. It'll be mentioned again in the 3rd lecture. The point to remember is the architecture is the same as in diamond. Now, there is another picture that I want to show you, a picture of a material which is in your body now and in my body, urea, U-R-E-A. Every animal, every human being secretes in his or her urine about 30 grams of urea every day. You can grow crystals of urea. Urea is an extremely important material. It's one of the best fertilizer material. It's also a very good material in laser science. If you have a crystal of urea and you allow a certain laser beam to enter it, when it comes out, its frequency is doubled. That's why people are very interested in urea these days. But it's also the backbone of the plastics industry. Every single button, I dare say, that's in this room at the moment is made of urea formaldehyde. And furthermore, There's no end of other uses that urea has. Substitute wood, for example. All the plywood that you now buy is urea formaldehyde. It's not wood that comes from a tree. Here's the crystal architectural structure of urea. Now, let me tell you, we're rotating it. Rotate it a little bit more, splendid. A little bit more again. That's fine. That's the crystal architecture. Now, what the scientist, what the chemist does, is to pull out from there one molecule. Let's do that, Andreas. I'm just going to pull out one molecule of urea. I have an example of it in my hand, and I have it on the screen. The red is oxygen. The black or the gray is carbon. The blue is nitrogen. The white is hydrogen. There is urea, that cluster, that shape, that group, if you like, of 8 atoms that moves like that, in that form, is the urea molecule. It's the urea molecule. Now, what I'm really telling you is then that the whole magic about architecture of crystals is that if you can grow a crystal, solve its structure, determine its architecture, you can get at the properties of the molecule. Now that means that the key components of modern medicine, the drugs that one uses, shall we say, to cure illnesses, to conquer cancer and blood disorders, these things, you can determine their structure in the way that I've described the determination of the structure of urea. That's how the strategy goes. If you wanted to determine what a vitamin, suppose you had discovered, vitamins were only discovered about 50, 60 years ago. You isolate them, you purify them, and then you form a crystal of them, and you determine the structure. Dorothy Crowfoot Hodgkin was awarded the Nobel Prize in 1964 because she grew a crystal of vitamin B12, determined by diffraction, this kind of experiment, the pattern that it generated, arrived at the structure, the architecture of the entire crystal, and pulled out the structure of the vitamin B12 molecule. The same is true of penicillin. The same is true of many other things. In fact, there's one particular material which I'm going to mention to you, but not before I ask you a question, which I just want to focus on. Now, what are the molecules or the materials, the substances in our bodies called that assist our body processes? You know, the digestion is helped. What do we call those?
Enzymes.
Enzymes. Spot on. First time. Now, an enzyme, thank you very much, an enzyme is a catalyst. It's a biological catalyst. What it does is speed up things. There's an enzyme in my eye and in your eye, in every teardrop, called lysozyme. You know, you've heard of electrolysis. Lysis means breaking down. Lysozyme means the enzyme that breaks things down. If I have any foreign bodies that go into my eye, or you have into your eye, those bacteria, those other foreign bodies that are there, have got to be cut up, smashed, smithereens, so that they don't destroy or damage the cornea. That's the function of lysozyme. The structure of lysozyme was worked out in this building 20 years ago. I want to show you what it looks like on the screen. Now, this is the static picture of lysozyme. Let's run this film. Look what happens. This is now being run. You see it? It's really quite an exotic dance that this molecule is executing, right? It's like an extraterrestrial rock dancer. You see it? That's what that lysozyme molecule, which is in your eye, there are millions of them in your eye, at this very moment, they're dancing like that. That's been magnified a very, very large number of times, about, in fact, 100 million times. Now, there's another molecule I'd like to ask for some more help in a moment. There's another molecule, a very famous name, I'm sure you've heard of it, the molecule that's in our blood. What's the main molecule in the blood called? The one that carries around the oxygen. How about it? Hemoglobin, that's correct. But a very, very good response. Right, now hemoglobin, I'm not sure, Bryson, whether the hemoglobin that we put in here today looks all right. Yes, that's reasonably good. Perhaps we can see that on the screen. There's a few small crystals of human hemoglobin, which we put there just before lunch. Now, what I want to tell you about hemoglobin is the following. Its structure is very, very complicated. It was worked out in 1962, another Nobel Prize-winning achievement by Dr. Perutz in Cambridge. The hemoglobin in the body of every single person here is slightly different. In some people, it isn't really quite right, and it gives problems. You've heard of anemia and pernicious anemia. You've heard of perhaps sickle cell anemia. Some people are born with a genetic defect. They've inherited it, and there's a problem in their blood. And if nothing is done about that, they would suffer grave illnesses. They might indeed die prematurely. So what the chemist has to do is to work out ways of conquering that problem. Now, I'm going to solicit some help, and I'm going to do something very strange. Now, you stand up. Put that thing on. Put that thing on. Tell me what your name is first.
Paul.
Paul. Right. Now, you've put your right hand in, Paul, and I'm going to put my left hand in. Good. Fine. Now, what you've just done there, just by putting your hand into a glove, you can sit down now, Paul. Thank you very much. What you've just done, and what I've just done, illustrates quite an important principle. See, we can't put any old shape. I can't put my foot in there. I've got to put my hand in there, and so have you. Now, if the heavyweight boxing champion of the world were here, he wouldn't get his hand in there, right? It would be too big. And if you had a little brother, age 1 or 2, it would be too small for that, right? So there's got to be a kind of neat fit. These can expand a bit. You notice that that expanded a bit as you put it in. Well, hemoglobin's a bit like that. Not just hemoglobin, other molecules, other biological molecules. This is the whole point about the way in which the research scientist designs drugs to cure illnesses. You see, what one does, one recognizes, if I turn to what's on the screen here, now this isn't quite the kind of drawing that you've seen previously, but it is nevertheless a greatly enlarged picture, the architecture of the hemoglobin molecule, which we've pulled out from that hemoglobin crystal. Now, what I want to draw to your attention is that there's a channel, that there's a groove, there's a recess running down that hemoglobin. If I could get a molecule with the right properties in it, but which must fit in there, it's got to be vaguely rod-like, therefore, if it could be inserted in there, then there's a chance that that molecule would cure the illnesses that certain people possess because of the deficiencies and the problems in their hemoglobin. Well, Dr. Perutz in Cambridge and a co-worker in Pittsburgh have done just that. If I now let this film run, watch what happens. We rotate that, first of all. We're looking at the hemoglobin molecule, or a small part of it. And now the drug molecule called bezafibrate, that's the name given to it, is going to be inserted there. Here it is in a skeletal form. In three-dimensional form, it's like that. That's the sort of actual size to scale. Now we're going to drape that with the hemoglobin, just as it is. When that drug goes into the hemoglobin, that's what you get. And it's because that molecule, that drug, can fit nicely, just as your hand could fit nicely into that glove, that works. It's not the perfect drug, I should say, because people are constantly exploring. They're continually trying to improve and find out better ways. See, the whole strategy of getting anti-leukemia drugs is exactly the same. you look at the enzyme, or you look at any other biologically important molecule. You grow a crystal of it first. Then from the crystal you get the nature of the molecule. And then you look at it and you decide what kind of shape should that molecule that you want to put in be. And you set about designing that. That's exactly the procedure. Now, there's one other molecule that I've got to mention because it is the building block of life: DNA. DNA, deoxyribonucleic acid, I'm sure you've heard of. But I wonder if you can recognize this woman here. Does anybody recognize that woman? Who recognizes that woman? Rosalind Franklin, a lady who was born in London, studied in Cambridge, came back to work in London, and in fact in King's College London produced what is shown on the next slide, one of the most important X-ray diffraction photographs in the history of science. It's the diffraction pattern of DNA. Now, for a long, long time, that puzzled people. It puzzled even the experts very profoundly. Why was it that one had a sort of criss-cross of dots? Why was that the case? Well, Bryson and I are going to illustrate to you why that is so. And I'm going to do so, first of all, by picking up this little model, this helical structure. That's a helix. Why have I done that? It's because what Bryson is going to pick up in a moment in this electric lamp light filament, we've broken off the bulb, there is a filament which is exactly like this. Now we're going to do laser diffraction. We're going to pretend that these are X-rays, and we're going to allow the beam to strike that, and there we are, just not quite there yet. There we are. We've got an intersecting crisscross, not quite as pronounced perhaps, but there we are, there it is again. Crisscross, rather similar to what we saw earlier. Thank you, Bryson. Now, that perhaps enables me to convince you that this model, which is one of the most famous in the history of 20th century science, and certainly the structure of DNA, which was finally solved by Crick, Watson, and Wilkins, is certainly one of the major triumphs of 20th century science. We have the helix. Here it is, look. The helix goes round and round and round and round. And then there's another one coming the other way, and so forth. Now, just as I was talking about putting a drug molecule into a little recess, into a little niche inside hemoglobin, likewise, there are scientists all over the world at present trying to conquer cancer, which involves, incidentally, multiplication of these DNA strands, furious multiplication, overproduction of them, by designing a molecule that can be inserted in here and that can stop that process. That's indeed what's going on in the science of molecular biology and molecular medicine at present. Well, at this point, I want to turn to a somewhat different tack, but not before I just recall where we've reached. Let me just remind you that modern man is a very ingenious creature. There are now 10 million organic compounds, most of which you can crystallize into beautifully shaped crystals. Most of them. 10 million of them. And they're increasing at the rate of something like 500,000 a year. There are something like 3,000 minerals. There are something like 200,000 inorganic material like rust or salt or cement or concrete or whatever. Now, we just don't have the time to solve the architectural structure of all those. There's no time, and furthermore, even if there were time, it wouldn't be sensible to look through every one of them. I mean, to describe me as a person, or to describe Russell, shall we say, as a person, fully, takes a long time. If I say to him, Russell, come down here, let me have your fingerprint, that takes no time at all. Well, now that's the strategy that modern man is adopting these days. What he does is to take the fingerprint of every solid that is prepared. He takes the X-ray fingerprint. Now, I'm going to illustrate that with the aid of a sort of detective story which involves a pigment known as Egyptian blue. Now, let me tell you, first of all, what this pigment Egyptian blue is thought to be, but we're going to try and find out what it is. And let me just draw to your attention this lovely lady. Does anybody know who she is? Has anybody seen that model before? How about you? Nefertiti. That's exactly right. The model, the head, the bust of Nefertiti was discovered in Egypt in 1912 by German archaeologists. It's still in Berlin. It was lost during the war, by the way, but it was rediscovered. And it's in Berlin. And this is a model of the cast, as it were, of Nefertiti, who lived in 1360 years before Christ. Now, I draw to your attention Nefertiti's bust for one very specific reason. This top part here is made in the real bust of the blue pigment Egyptian blue. Now, Egyptian blue was used for 4,000 to 5,000 years as one of the best pigments that man had ever found. The Greeks used it after the Egyptians, so did the Romans, but then, with the demise of the Roman Empire, the secret of how to make it was lost. Now, we're going to try and recover that secret, so we need 2 volunteers. I'm going to have one boy and one girl. Let's have this young lad here. Come along, all right? And one girl. You come along, all right? Fine. Now, what's your name? Sam. Sam, I want you to accompany Professor Phillips, but not before I give you a sample of Egyptian blue. I'm going to ask you to go down to the basement to our X-ray machine. We'll see you on the screen, on the monitor, after Professor Phillips has taken you down there. It'll take a little bit of time. Now, what's your name?
Beth.
Beth. Now, Beth, I want you to come round here. Beth, I want you to help Paul. What we've got in here, Beth, is a sample of Egyptian blue. I'm going to ask you and Paul, first of all, to get us a good picture of the mineral, of the pigment rather, and then I'm going to do something else. We're going to try and find out what the building block of that material is. Let me explain. You go ahead, Paul, and explain to Beth how the machine works so that she can help you. In the meantime, I'm going to tell you that this instrument, this extremely powerful instrument, is not only capable of producing wonderful pictures, as you've seen already, it's also capable of detecting the X-rays that come off a sample when electrons hit it. When electrons hit anything, if they're powerful enough, they generate X-rays. Now, there we are. We're looking at the Egyptian blue. That's very good. My gosh, it's just like a bit of ash from the moon, isn't it? See, color has no meaning when you look at things under this magnification. Nothing has color. You're beyond color when you look at it under there. Now, Paul, I wonder if you and Beth can bring up a spectrum for us. Can you bring up an X-ray spectrum telling us what constituents there are in this Egyptian blue? This is a very clever method. There's a detector crystal of silicon in there, which is able to spot, that's right, look, silicon, calcium, copper. We're actually building up the signals. We are knowing directly what's inside that pigment. In fact, the story, you can stop there. I think that's fine. We can stop there. Beth, that's very good. Thank you very much for your help. Now, the point I want to make is that we've now discovered that in that Egyptian blue there's calcium, copper, and silicon. I should mention to you, by the way, that one of the great men of the Royal Institution, Sir Humphrey Davy, in 1815 was sent a piece of Egyptian blue from the ruins of Pompeii. And within 2 or 3 weeks, using his wet chemical methods, he also concluded, and he was right, that it was made of calcium, copper, silicon, and oxygen. Now, before we join our friends down in the basement, there's one other thing that we still have to do, because you've got to understand how we fingerprint solids easily these days. Bryson is going to redo a very famous experiment, which was first done in the University of Aberdeen in 1928. We have inside this evacuated tube a small piece of graphite, polycrystalline graphite, lots of little crystals in various orientations. Bryson is going to accelerate electrons through that. And on that screen, when the lights are dimmed, you will see that we have beautiful rings there. There's a ring pattern. I don't think there's much doubt that there's a ring pattern there. All right, well now that's electron diffraction telling us that when electrons go through an aggregate of crystals, we get a ring pattern. If we do the same with optical diffraction, if I take this pattern here, hold it to my eye, what you should see on that screen is exactly what's there. Let me give this to Bryson in the meantime. You can put it into the beam, Bryson. What I've drawn to your attention is that there's a crystal here, there's a crystal there, and there are many crystals overlaying one another. It's polycrystalline. Now what Bryson is going to do is do optical diffraction. And we should have a ring pattern there. I hope we do. Is that visible? Just about visible on my screen. Just about visible. That's fine. Well, that's it. Look, if you were to take a photograph of that, if I could have the lights up, please. If we could have a photograph of that, what we would really see is what I've got behind me here. Any crystalline powder, when you have diffraction, gives you a pattern like that. That's called a diffraction pattern, obviously. If I take most of this away, because most of the information here is redundant, I need only leave a small bit, and that small bit tells us a lot. Here's the bit of the diffraction pattern, and what I've now done here is to convert that picture of lines which are intense, slightly less intense, slightly less intense, intense, substantially less intense. And now I've plotted intensity against position. You see that and that are about the same intensity. These are lower intensity. In other words, any material has its characteristic fingerprint. If we do a diffraction experiment, as I hope they'll be doing downstairs in a few moments, if we do a diffraction experiment, we will get such a pattern. Now, my student, Ingrid Pickering, should have by now received our young friend. Yes, she has. Good. Well, you go ahead, Ingrid.
And I'm taking the sample of Egyptian blue, and you can see the blue pigment on the disc. And I'm going to put it into the X-ray machine. There we are. Now the X-rays are generated here and pass in a beam down towards the sample here, and then are diffracted up to the detector here. Now if you could push this button here. That's it. Right, now that's finished there, so if we'll go through to the other room.
Well, now Ingrid has got to the computer terminal in the room next to where we had the X-ray diffraction system. And what she will be able to do shortly is to produce on the screen there the diffraction pattern, the fingerprint, the characteristic fingerprint, we hope, of Egyptian blue. That will appear shortly, and then we have to try and see whether we can identify whether it is indeed copper, calcium, silicon, oxygen. Now, to do that, we have to dialogue with a database, a computer database. There we are. Ingrid, can you place onto the screen the Egyptian blue diffractogram? Very good. That's splendid. Now there's a database in Philadelphia, in Bryn Mawr College, Pennsylvania. We have a copy of that database in the basement. What I want Ingrid to do is to pull out the X-ray diffractogram of the copper, calcium, silicon oxide, which we found with Beth's help is present in Egyptian blue. Can you bring that out, please, Ingrid? Excellent. You see, each of these purple lines certainly coincides with a peak. But those of you who are looking very carefully here will find that there are one or two peaks which don't have lines corresponding to them. Now, the reason for that is we have a little bit of impurity in that Egyptian blue. In fact, in Egypt, there's no shortage of sand. In fact, silica, the sand, is quartz. Could you put in the fingerprint of quartz, please, Ingrid? That's fine. See, and these match up. So there's now an improved correspondence. We could dialogue further with the database and we would know exactly what's there. So that illustrates the power of our being able to identify materials just by looking at their fingerprints. Just as the police would identify a potential criminal from his fingerprints, or her fingerprints. Now, I want to take this opportunity of answering a question which I said was very difficult to answer when I spoke in my first lecture about what is a crystal? When is a crystal not a crystal? Quartz is a crystal, right enough. Here's quartz. The real proof that it's a crystal comes from the fact that it's got a sharp diffraction pattern. Obsidian, which the primitive man has used, here's the Stone Age axe, which I mentioned in the first lecture. Obsidian is chemically very similar to that. It looks different, but it's very similar. It's largely silicon dioxide. But it's a glass. It's not a crystal. Why do I say it's not a crystal? Because it is a very diffuse diffraction pattern. In fact, there's an animation that we've got here for you. Watch this very carefully. Shortly on this screen, we show you quartz again. We show a part of the quartz, and now we show you the characteristic diffraction pattern. Let's compare that with what comes next. Next, we're going to show obsidian, which is a very diffuse pattern. That's the diffraction pattern, one broad single line. So that's how we know the difference between a crystalline and a non-crystalline material. Now, at this point, I want 9 volunteers, 9 of them. I want 3 from this side that haven't come out before. You come. What about you in the second row? And what about you in the 5th row? Come along. 3 from here. Good. What about you, first of all? Would you come also? And what about you also? Fine. What about here? Good. Fine. You come along. And the 2 of you there, come along. Now, I want you to form 3 rows of 3 people. You come and stand here. What's your name?
Thomas.
Thomas. Come on, Thomas. You face this way. What are you? What's your name?
Ben.
Now then, Ben, face this way. Face me. Come along. What's your name? No, this one. Helen. Now then, you line up behind. Line up behind. No, face there. Line up strictly behind, right? 3 rows of 3. 3 rows of 3. Be like guardsmen on parade. That's it. 3 perfect lines there. 3 perfect lines. You're going to be atoms. Some atoms are bigger than others, okay? All right, now 3 rows of 3. Now what I want you to do is stand still, just as if you were guardsmen on parade. Shortly, not yet, music will play. When the music plays, I want you to dance. I want you to move around. Oh? I don't want you to bump into one another. You can even move away from your territory a little, but you mustn't touch. That's the only rule. You mustn't touch. You can gyrate, you can do anything. You can stand on your hands if you wish, but you mustn't touch somebody else. Right, now when the music starts, you're going to do that. When it stops, you stop exactly where you are, even if you are standing on your head. Right? You've got to stop exactly where you are. Right, the music should begin. Fine. Off we go. Come on. Give us the benefit of being in a discotheque. Come on. All right, good. Come on, move around a bit more. Oh my goodness me, it's not very accurate. Right, stop! Oh my goodness me, look. You are supposed to be disordered. You're partly disordered. You are very disordered in this part of the crystal. This is what I would call a glass. But over here, these 3 are still in the crystalline state. They're very much in the straight row. Well, there we are. That's the principle I wanted to illustrate to you. You see, look, there's quite a big gap between these 2 here, and quite a big gap here. That's why in a glass, you can put other atoms in. You can dissolve things into a glass. That's why they, incidentally, bury radioactive waste in glass, because there's room for it, you see. Thank you very much. You go back to your places. Very good. Now, I want to show you a very quick snippet of film which has been done on computer. It's going to illustrate how a solid, these atoms are in a solid, in a crystal. Now they're about to melt. I'm increasing the temperature. And here they are in the center here. As I'm increasing the temperature on computer, this region has melted. That's still a bit crystalline up there. That's melted. Now, I have to leave that because I want to show you, with the aid of Bryson's assistance, something that is very ingenious, which Lawrence Bragg and his student Nye developed. This is known as the bubble raft. I want you to imagine, as Bryson is perfecting this, that each little bubble is an atom. And what Bryson is now doing is generating atoms. He's blowing bubbles. Each one of those, you see, is moving off as rafts. He's like a trained ringmaster here, aren't you? Look, pushing away 2 or 3 or 1 or 10 or 20 clusters of atoms and building up a sort of polycrystalline region. That's not a nice, well-ordered crystal. It's quite ordered, but not very well-ordered. That's like the polycrystalline graphite that we had that gave rise to those rings. That's very nice, Bryson. Thank you for showing us that. Now, I want Paul to help us next on something really rather adventurous. I'm sure that many of you have been puzzled by this object here. This is a beautiful opal, an Australian opal. Very, very nice. Opal has spheres in it, spheres of silica, silicon dioxide, which are so small, they're 1,000 times as small as those bubbles that you saw in the raft. Now, the British Museum would not allow me to chip a little bit of that off, naturally. So what we did instead was to take artificial, man-made opal, made in Malvern. And what Paul is now going to do is to zoom in on an aerial kind of flight, as it were, into this opal. Well done, Paul. That's a very nice picture. See, look how smart, look how beautiful that picture is now. You can regard these little spheres as atoms. And there are ledges and terraces and one sort of row or plane of atoms above another. Rather well ordered, slightly disordered there, sort of glassy region there, very crystalline region there. You can move around and tilt it. That's it. There we are. Beautiful opal or man-made opal. Lovely array. See, this teaches us a lot about what we believe crystals are really made up of. We haven't quite reached that level, but wait. Thank you, Paul. I've got one very important movie clip to show you, which is coming up next. This is a high-resolution image, here it is, of growing gold crystals. Watch very carefully. Here are individual atoms of gold. Individual atoms of gold adding themselves onto those ledges. That's a magnification of about 100 million, effectively. Individual atoms of gold being magnified and recorded dynamically. Absolute poetry. Now, there's one thing else that I want to show you. And this I couldn't have shown you if I were giving you the Christmas lectures last year. Bryson, you go ahead. You leave that magnet, let it rest, let it fall. Look, it hasn't even fallen. Look at that. That's real magic. We'll tell you more about that next time. Thank you.